Hello, my name is Santiago Avila. I'm a postdoctoral researcher at IFA in Barcelona. And today I'm going to talk about how the Dark Energy Survey measured baryonic acoustic oscillations from its final dataset. So, brief introduction, baryonic acoustic oscillations originate when some sound waves propagate in the early universe up to the era of the coupling. So this creates an effect in which we have an original overdensity somewhere, and then radius around it, we will have this sound wave that will arrive there, and then we have an overdensity over here as well. This leaves this pattern of excess density and the matter in the large scale structure, and we can detect it as an excess of galaxy pair counts separated by this particular distance. Because we know how much this wave travel in the universe, we can use this as a standard ruler and basically determine the distance to redshift relation based on these measurements. These tell us about the expansion history of the universe, like H naught, omega matter, omega curvature, how much dark energy we have, and what type of dark energy we have. So the Dark Energy Survey is a photometric galaxy survey that observed for 6 years over 5,000 square degrees in 5 bands, G, R, I, Z, and Y, detecting hundreds of millions of galaxies with shapes and estimates of the redshift based on these bands. This is up to redshift 1.4. And this is the area that observed in the southern hemisphere. So the goals of the Dark Energy Survey is to constrain the nature of dark energy and other cosmological parameters with 4 probes: Type 1a supernova, baryonic acoustic oscillations, weak galaxies in combination with galaxy clustering, and galaxy cluster number counts. So the supernova results came out in January this year. I'm not going to talk about them, but you can go and click on this link and find out more. I will be talking about baryonic acoustic oscillations, which was also released earlier this year in February. And I will be talking in detail about this now. In the near future, we expect to release the final analysis as well from the weak lensing combination with clustering, so correlation of position of galaxies in combination with shapes of galaxies and the cross correlation. And we expect to improve over year 3 analysis. This is some forecast by David Sanchez, but so stay tuned. And also galaxy cluster count should come out in a similar time scale. Okay, so the Dark Energy Survey is a big collaboration with different countries led by the US in particular with Fermi Lab, NSF, and DOE. But then basically we have contributions from UK, Spain, Germany, Switzerland, and Brazil. Also we have the observations from the Cerro de Oro Inter-American Observatory in Chile. So in particular, I want to highlight some people that worked in the BAO team, but of course, this is a collective effort of hundreds of scientists that made DES possible. And the BAO team, myself and Anna Corredon have been coordinating this team and the large scale structure science working group. And then we have Juan Mena, Wukamacho, and Quan Chan that led 3 different analyses on the BAO. We have Ismael Ferrero, who constructed the mock catalogs. On the systematic team, we had a lot of people, including Martin Rodriguez Monroy and Noah Wiberdick. On the redshift team, we had also quite a few people, including Juan de Vicente, Julia Giannini, Laura, and Ross. Okay, let me start with some of the main ingredients, which is the BAO sample. This was described in a separate paper led by Juan Mena. And basically, we use a subsample of the full DES sample that has been optimized for BAO science. It's a red selection given by this selection in color space. We also select galaxies between redshift 0.6 and 1.2, where we expect to be competitive. We do a bright selection in order to make easier the validation with external datasets. And also we include another cut in magnitude in the I band that depends on redshift with this linear relation, and these 2 free parameters that then we optimize with some Fisher forecast, taking into account generating the samples and looking at the properties of these samples to generate this Fisher forecast. Additionally, we have some quality cuts and mass cuts that eventually we arrive with 16 million galaxies over 4,000 square degrees. And this sample is split into 6 tomographic pins given by a width of around 0.1 in redshift. One important part is to correct for systematics from LSI systematics. We use this code called ISD, Interactive Systematic Combination by Martin Rodriguez, that corrects for different foregrounds and observing conditions. So for example, if some patch of the sky has more depth, then it's easier to detect more galaxies and others. And we need to correct for these things and also like stellar contaminations and things like that. So we identify a list of potential survey probability maps that can be including the systematics, 23 of them, relatively independent. Look for the map that correlates the most with the galaxy density. And if this correlation is above some threshold, then basically we correct for that with a linear regression, and then we do an inverse weighting, and then we basically eliminate the trend with depth in this case. So each of the redshift pins is treated as a separate sample, and we need some weights for different maps in these cases. Then an important piece is also the redshift calibration. So we split our sample in these 6 pins. This is the tomography we referred to. But then, of course, even though we put like we try to do like hard edges on these tomography beams, we are trying to estimate galaxies, redshifts, or the spectra with these 4 points on it, right? So this is very hard, and even if we put like some vertical lines on the edges, eventually things spread because each galaxy has some error, and we end up with this kind of distributions. Okay. So how do we determine this distribution? This is quite hard, actually. We have different working groups and analysis teams working on this. But eventually, basically, we combine 3 independent methods, one based on machine learning, DNF, by Deviation et al. Then we have some direct calibration with the spectroscopic samples Vipers. And we also do some spatial cross-correlation with the spectroscopic samples from SDSS, and this is WZ, that was done by Ross et al. And each of them give us different estimations. So eventually we combine them together, and these variations also allow us to estimate some error that might be coming from these possible variations of the different NFCs. We see that this error is well below the statistical error bars, and eventually we end up with these 6 tomographic pins with these redshift distributions. Okay, on the methodology side, we consider 3 clustering statistics: the angular correlation function, the W theta, which basically we count separations of galaxies in the sky by a given angle. And then we can also basically project the sky into a harmonic space and compute the CLs. This is led by Hugo, and this is one led by Juan. And then we have the projected correlation function led by Juan, in which basically, instead of computing just angular distances, we transform the positions and redshifts of each galaxy to a coordinate in X, Y, Z, and then compute actual distances and so on. And eventually compute the transverse direction distance, so this one over here. So we don't take into account this one because this is very badly determined because of the redshift uncertainties. Then we have a fiducial template, T, which is based on the Planck cosmology, then the data redshift distributions and the data amplitude of clustering. So this is what we call the galaxy variance. And once we have this template, which is basically our 3D prediction, let's say, we can modify to have our final model, because in the end, we only care about the position of the peak. Okay, so how do we do that? We take the template and we can scale this template up and down with this parameter B, really. And then we can scale it left and right. So this is our template here in orange, and we can move it to the right or to the left, and it will match the data. You can see that in blue, we are matching the data here. Okay. So how we do that? With this alpha factor, okay? This alpha will move the template to the left or to the right. And then we include some extra parameters that we call broadband terms that basically take care of anything that doesn't look like a peak. So it's polynomial, and removes systematics and other things. So eventually all the information is in this alpha, so dm over rd, and then compared to the same ratio in Planck cosmology. So if alpha is 1, basically we recover something compatible with Planck cosmology. And eventually we combine the information from the three measurements together, taking into account the covariance in this what we call average. Okay, an important piece is to have mock catalogs. We have around 2,000 mock catalogs that are based on this I-Scola method by Ismael Ferrero, and that they basically reproduce the footprint of the survey, redshift distributions and uncertainties, and of course the clustering amplitude, as you can see here. Mocks are a key ingredient to validate the modeling. So again, we validate the modeling with these mocks, and we eventually we create a Badger error, which is well below the statistical error bar. And this will also help us a lot to identify features in the data. So we find something that we're not sure if it's by chance or it's not systematic, and then we run it on this analysis in the mocks, and we find, oh, this happens actually 20% of the time. So this is quite normal. So this is super useful. An important ingredient in DES is that we always want to avoid confirmation bias, so we always had a very strong blinding policy. The pool analysis was, and the paper was writing while blinded. Even the internal review was performed while blinded. And some tests were considered pre-blinded. So how we detected BAO globally? Let's say yes. Do we detect it in each of the individual bins? 5 of them. One of them not, but this is compatible with 20% of the mock, so this is normal. In our measurements, because the signal to noise decreases when you only have one redshift bin. Then we check if the measurement is robust to removing some redshift bins, as we do here. We see that it's robust, okay? And then we check what happens if we change the analysis choices, like changing the template cosmology, changing the covariance, or changing the redshift assumptions. And we see that things are very robust. Of course, we check also the 3 estimators, angular correction function, CLs, and projected correction function, and they are also compatible with our combination point, which is here. Once we check that everything was working well and making all these plots blindly, so moving the alphas by a random factor and so on, then we unblind it. Again, we end up with this measurement moving by this random factor, no? So eventually we find out that we are around 2 sigma away from Planck, which is 1 here. What does the clustering look like? So this is a BAO signal that we found, angular correction function like that. So the farther away, higher redshift over here, has a smaller angle on the sky. And as we get closer, we have the peak closer to here. Okay, remember here, we're trying to fit all the template together with all the 6 pins all together. So we're moving them together, all right? And we're not trying to fit each of them individually. So sometimes you might see that the peak is not quite perfectly fit, but that's normal, okay? Because we're trying to fit them all at the same time. So different points might be pulling in different directions. Okay, then in the angular power spectrum, what is a peak over here becomes some wiggles. And on the projected correction function, basically, we're now looking at moving distances. So the ruler stays the same, let's say, right? So we always expect the peak to be in the same position in moving distances. And that's what we find. Okay, so this is our 3 signals of the BAO. And then if you're wondering, okay, why don't you actually do it bin by bin? Okay, we want to have large signal to noise, and if we do it bin by bin, we have smaller signal to noise. And that's why, for example, in the bin, if we try to do it bin by bin, on the first bin, we don't have a detection. And this is where we get bin 2, bin 3, bin 4, 5, and 6. So we checked that all the fluctuations across redshift bins is compatible with basically random fluctuations by checking this on the mocks. And we also check that the low alpha value is not driven by the higher redshift measurements. It's actually quite of the opposite. It's the ones that prefer the lower values of alpha. In case you want to see how is one signal, one BAO, if you want to compress all the 6 pins together, we can do this only with the projected correction function, because in this case, all the peaks align. So even if you put everything together, you will get even a bigger peak or a bigger signal to noise for the peak. This doesn't happen for angular correction function because the peaks kind of cancel out, no? Or smooth out. Okay, so this is what we find. Is a template, and this is the best fit measurement. You can see like a clear detection of the peak. This is around 3.5 sigma. And this is the likelihood of all the measurements combined, all the individual clustering statistics, and then the combination in average here. And this is what you see, the 3.5 sigma line. This is if we didn't have a BAO in our data. Okay, so we checked that the results are robust. This is our measurement, including statistical and systematic robust, or the total one. We are around 2.1 sigma away from Planck. We checked that there is very robust to different clustering estimators. So the orange point, which is our consensus measurement, average measurement of the three, is very compatible with W theta, CLs, or project regression function. We checked that it's robust to like analysis variations, like changing the covariance that we assumed, changing the scale cuts, changing the cosmology we assumed, changing the data calibration, so ignoring the observational systematics that's not affecting the BAO position, or changing the redshift assumes that also is not changing the BAO position. So this is very, very robust, and our consensus measurement seems to really be the consensus of all these variations. Then this is the BAO angular distance ladder at the end of stage 3. This is our point. We have improved a lot over with respect to year 1 and year 3. And we are competitive with other spectroscopic measurements from stage 3. So this is BOS and EBOS that were designed for this purpose. Okay, so this is very impressive. Our point is at 0.85. And we are 4% more or less below Planck. So it's the most precise photometric survey, and is the most precise beyond redshift 0.75 in this plot. So more precise than these other ones, which was the most up-to-date plot when we published this. We now have measurements from DESI 2024, and these are point compared to the other ones. We see that we are still competitive. Other ones have been smaller, but this one is very similar to the LRG2 point, and is actually in a similar level of tension with Planck that our point. So this is very interesting to see what this is telling us about the universe. So in summary, DES measured the BAO at an effective redshift of 0.85 with a 2.1% precision. It's very robust to many different things on the observational, on the modeling, and on the human side. We are in slight tension with Planck, and we have made competitive constraints with the stage 3 and stage 4 experiments, even spectroscopic ones. This settles the basis to do precise and accurate galaxy clustering with photometric surveys, and we will keep in doing that with primordial non-Gaussianities, in combination also with weak lensing, combination with other probes like galaxy clusters or CMB, and eventually doing and completing the multi-probe cosmology that was planned with DES. Thank you.